discussing a presentation by Andrew Ilyas. He's now at Stanford, and it is using influence functions to predict model behavior and optimize across models. So let me parse that a bit. So influence functions are an attempt statistically to measure how certain components change a model. So for example, certain input components change a model without having to retrain the whole model. Andrew also offers in other presentations and papers an ability to edit models without having to retrain them. So the key motivation of his work is really two things. One is you have a vast design space of models these days. You have the whole pipeline, right? The whole stack, the whole machine learning stack, which is the data that you're using to train. Then you have the model, and within the model, you have all kinds of components. So whether it's if you use transformers, you have different heads, attention heads. You have convolutional neural nets where you have convolution, so you have masks, or you can even combine them. So there's different types of components of models that influence the model itself. And I want to calibrate this a little bit with what's actually going on in the real world. And I think this is one of the more important tasks that the real world AI engineers face, and that is how to optimally train a model, how to optimize the design space of what data are we using, how are we cleaning the data, and then what model are we using. And Elon Musk said in one of the conference calls, I believe, recently, that one of the problems of Tesla AI is how to evaluate models, because the training of models takes a long time and it's very expensive. And if you have certain design space decisions to make, whether you want to have certain, learning parameters or filters or attention blocks, whether you want them, parameterized this way or that way, these are important decisions to be made that could have an influence on the model. And the key of Andrew's work is really to formalize all these decisions and offer a possibility to make those decisions prior to the training. I want to discuss this approach. I think it's important. Also, I want to say that some of the most important presentations that I've attended recently, in whether it's at conferences or whether it's at Stanford, it's usually about statistics. And I think statistics is kind of getting a little bit of a bad rap here. It's considered almost a sideshow of the big picture stuff, which is the AI or let's say biostatistics. But in many cases, statistics is the show, and the application in whether it's predicting, self-drive, or it's predicting the next frame in a self-driving car or predicting the next word in an LLM. I mean, that's the fun, right? That's why we're doing it. But the show is the actual stats. And things like influence functions that Andrew talks about are really, really key to understanding how data input influences a model prediction, and also how models can be attacked, or so-called backdoor attacks. So I just want to say, for people that listen here that might be in sort of thinking which part of the AI stack they should optimize for, or maybe spend some more efforts in, or things like that. Actually, statistics, I would say, is one of the things you want to spend a little bit more time. If you're thinking about doing a master's or a PhD, I would say statistics is not a bad place to be. It's a dry area of AI, but it's a good base to have. For example, Percy Liang, who's a very impressive researcher and talks about really important things about ethics, about alignment, about all these kinds of things that are important. But his base, his real work actually is in statistics, and it's, he wrote a paper about influence functions in 2017. Links in the show notes, that I believe is sort of set the foundation for for machine learning to actually use these types of models. This is not even on podcast. It's October 22nd, 2024. This is Krimdelko. For the year, we are up 15.3%. The market is up 22.6%. We're underperforming by 7.3%. So I'm talking about Andrew Ilyas. He's a Stanford researcher. I believe he's a postdoc or associate professor at this point. So the problem is estimating and optimizing counterfactual behavior of large-scale predictive models. So what does that actually mean, right? Determine which version of the model and which data is optimal for the desired results. Counterfactual just means, what if we use this type of input versus that type of input? What if we tweak this part of the model versus that part of the model? And I wanna sort of champion this problem with Musk's words. That he said one of the big problems that Tesla has is to actually evaluate which model to train. In particular, when you do end-to-end training, right? When you do what FSD looks like, you want to understand which training data improves the model, and you might also want to understand which parts of the model could be improved given the data that you have, and which parts of the model maybe you don't want to change, or which data you don't want to change. So when you train, maybe you can, maybe you can do this kind of goes into the direction of continuous learning. Okay, you don't want to have you don't want the model to forget. You want it to sort of build on top of what it already knows, and those are the kinds of problems that Andrew's work is touching upon. So let's talk about influence functions. So influence function, there's a paper by Percy Liang, links in the show note, that goes back to an influential paper in the 1970s. So influence function, the way I understand it is the following. Like, you have a bunch of data which influences the statistical model, or in modern terms, the machine learning algorithm, right? So the data that you're actually putting in will determine the outcome, right? It's garbage in, garbage out. We've heard that many times before. It's like that in machine learning. It's like that in statistics. And what you want to understand is, like, which parts of the data influence the model how. And with influence functions, you can do this without having to retrain the model all the time, right? And the way you do this is by infinitesimal changes of data inputs, and then just linearly extrapolating from there. So you don't have to retrain. You can just say, okay, what if I take this piece of data and I change it a little bit? How would it change the model? And if you can analyze those gradients, and then you can see, okay, well, over here in this region, I have a little bit more gradient than over there. So this type of data seems to be more influential. I think that's kind of the way I understand it. We're talking about first order and second order derivatives. We're talking about Hessian functions, Jacobian functions. That is technical. I don't want to talk about this, but think about it just in very simple terms. You have a very, very large matrix, but you can sort of just linearly calculate data input and its gradients with respect to the actual function that is doing the prediction. And if those gradients are large, that means that the data, the inputs, the inputs with large gradients, they have a large impact on the model's prediction. This is what an influence function to me looks like. And I think it's the key is, again, you don't have to retrain the model every time you change something in the data. I think also, as a side note, this goes back to the importance of actual data management, right? Machine learning is really all about data, but it's not just about having clean data. It's also about deciding what kind of data do I even want, right? So in the case of Tesla, Do I want to have highway driving, I want to have city driving, but maybe I don't want to have data where there's cows on the road. Even though that could be interesting for that particular case, maybe it will change certain parameters in the model and make other things worse. So you want to understand the impact of that particular input, and if it doesn't have too much of an impact on the general performance of the model, then you can keep it. Otherwise, you want to take it out. So that is again the influence function. Now the other part of Andrew's work is the optimization. So this is now the problem of, okay, how do I know which model version is the better model? And again, the motivation for this is I don't have the luxury to train many models simultaneously for months and months. It's expensive, and then decide which one is better. I want to be able to a priori decide which design space I should use for the training once I deploy it. And even though people like Musk and Grok and XAI and NVIDIA and Meta and all these people, they do build out massive GPU clusters for training, and some of it is actually to have more model iteration. It would still be much better to have sort of an a priori decision-making process where we can decide, okay, which parts of the model are better, how do we edit the model? And what Andrew proposes here in the paper, again, links in the show notes, he proposes sort of a component analysis. The way I understand this is, let's say you have, let's say, a convolution layer, or you have an attention block in the model, which would be a component. You have many such components. You have things like heat, temperature, lots of parameters that you could play around and tweak the model. And you want to have some formal statistical way to optimize those parameters a priori. And the way you could do this is, again, through some sort of infinitesimal gradient-driven statistical analysis. So in other words, kind of like a marginal utility analysis, where what if I change this a little bit and keep everything else the same? What if I change this and this? What if I change those three but change the other one? Like those kinds of things. And I think this is incredibly important because it also allows model iteration. Like what we want in general, now let's take a step back. What we want with machine learning pipelines is to have rapid iteration. We want to get better and better at it, and we can only do this with rapid iteration. I think Andrew's work is helping us to iterate around the data input and iterate about the model design. Lastly, also important, his work is also important in two ways, in two additional ways. One is deterministic machine learning. So we want to understand which parts of the input influence the model. So that is good for things like alignment. That is also good for things like safety, although I have my doubts there that that can be misused. So I'm a bit critical about that, but still we want to have, we don't want models to do stupid things, particularly in the robotic space. And then we also have the problem of backdoor attacks. So in other words, we could have agents, malicious agents feeding bad data to a model. So we could, famously, I think so in the mid 2010s, there was this problem of, the Swiss guy that talks about papers, I forgot his name, Yannick, something like that. I think his PhD thesis was about that, about GANs and how you can manipulate them with very small variations in input data that can change the prediction of a model dramatically. So you have, let's say, 3-4 pictures that look very similar, but a few of them have certain things, certain patterns in their pixel space that dramatically changes the prediction of the model. So to be able to capture these things, understand them, and deterministically also design the models so they are not vulnerable is part of the goal. So to summarize, I think statistics is the show in AI. Like it or not, this is the bad news. for people maybe that want to study AI and get into the field and think that, oh, it's all about talking about ethics and fairness and all that. If you want to study ethics and fairness, go to the philosophy department. The problem in AI is often very, very technical and statistical. In particular, the problems that Andrew Ilyas talks about, which is, again, how can we optimize the design space of machine learning pipelines? What kind of data should we use? Which data should we include? Which data should we ablate? And then also, what kind of model design components should we bring in, should we ablate? And finally, also, how can we have a more robust and deterministic machine learning pipeline where we know what kind of input will have what kind of output? Thank you.